All right. So today I will be presenting on the atomic absorption of conjugate dye molecules. The dye molecules that which we are looking at are here below. The names are kind of a mouthful, so throughout the experiment, I'm just going to refer to them as dye 1, dye 2, dye 3, and dye 4. So we got a lot to go through, so I'm going to try and be quick. So let's go ahead and get started. So a brief introduction. So why do we care about dyes? Well, dyes color our food, they color our shirt. They're all around us in everyday life. But what's so important about these specific dyes? These dyes allow us to investigate the electronic absorption and electronic energies between the HOMO and the LUMO, because as light hits these dyes, an electron jumps from the HOMO to the LUMO, and we can calculate that energy based on the maximum absorption wavelength, which I will get into shortly. So just quickly about the dyes, these dyes are cyanin-based dyes, where the portion highlighted in red is the conjugate carbon chain, which gives rise to the color of the dye. The electron excitation between the HOMO and the LUMO occurs upon light energy hitting the dye, and each dye contains two cyan moieties, which will measure how the energy gap difference depends on the length of these cyanin moieties. So as I mentioned, these dyes, they absorb in the visible region. So here is a spectra of dye 1 from our experiment, and here is the visible spectrum. And as we can see, this dye absorbs at around, like 425 nanometers, which is like in the purple area. So the color of this dye is most likely like an orange or a yellow, but we can see where it absorbs here, and we can use this peak wavelength to calculate the difference between the ground state and the first excited state. So our hypotheses, we hypothesize that dyes with longer conjugate chains will also absorb at higher wavelengths because the extra pi electrons allow for more absorption of light. And we also predict that predictions made through Cygress, the modeling software, are more accurate because Cygress takes into account more than just the 2p electron delocalization. So quickly, let's go over the methods. So here's our experimental setup where we have a light that travels through a lens, hits off a mirror, travels through our sample, travels through another lens and into the detector. And essentially what's going to happen is as the ray of light passes through the cuvette, an electron will get excited from the HOMO to the LUMO, and it'll produce a spectrum, which we can see here. So that's basically our experimental setup. Quickly going through variable definition. So delta E is the transition energy between the HOMO and the LUMO. The lambda max is the maximum absorption wavelength. Beta resonance, or beta is the resonance integral, which is used to calculate energy levels based on coefficients, which we'll see later. And delta coefficient is the difference in energy of the HOMO and the LUMO in the units of beta. So quickly going through computational methods and predictions, our first one is the particle in a box. This is the most crude method where we use the calculated energy of a particle in a box to calculate the transition energies as well as the maximum absorption wavelength. Here, these are just the constants, the quantum number, Planck's constant, mass of an electron times 8, and L is the length of the box, which I have highlighted here in red. And we can use this to make predictions, very crude predictions about the energy transition from the HOMO to the LUMO, as well as the maximum absorption wavelength. Next, we went over the Huckel molecular orbital model and the Huckel matrix. This is a complicated method that uses linear combinations of atomic orbitals to produce a matrix that looks like this. And when you solve the determinant of this matrix, you can solve for energy values. But what's difficult about this matrix is that these H sub 11 and S sub 11s are difficult integrals. So as chemists, we use a thing called the Huckel approximation, which creates a matrix that looks like this, where we treat interactions between non-neighboring atoms as 0 and interactions between neighboring atoms as a 1. And then we fill the diagonal with the beta, and we solve for the diagonal using the determinant. And that gives us those beta values, which we can use to make those electronic transition levels. So here's an example with butadiene. We can see that we create this matrix of neighboring and non-neighboring atoms as 1 and 0s. We have these x's. We would take the determinant, solve the x's, and we would find that x is equal to 0.62 plus or minus and plus or minus 1.62. And then we're able to construct this energy level diagram, E1, E2, E3, E4, with these various beta levels, where this is the non-bonding orbitals, and these are the bonding orbitals. And this is just the Python code that I use to calculate the beta values for the various dyes that I just wrote this Python code real quick. So lastly, we looked at the Hartree-Fock approximation, and this is really complicated math, so I'm really not going to go into it too much, but really all you need to know is that in this Schrodinger equation Hamiltonian, this term is really, really complicated. It makes the math really difficult. So Hartree-Fock simplifies this down to this term. It's still kind of complicated, but it's simpler than this term and easier to do the math behind it. And we're able to get this final Hartree-Fock energy, where these are integrals right here relating to the molecule, still kind of complicated, but less complicated than the original Schrodinger Hamiltonian. And we're able to calculate various things based off of this using various types of Hartree-Fock approximation methods, which I'm about to get into now. So these methods that we use that are available in SciGrass, these Hartree-Fock approximation methods, are based on various things from MOS, which is a semi-empirical molecular orbital package to calculate the spectroscopic properties of a molecule. As I said, this is available in SciGrass, so we're going to be using SciGrass to run all these different types of methods and predict our electronic spectra. So here are the methods: MNDO, AM1, RM1, and PM3. I'm just going to quickly go over these. MNDO employs a key approximation of neglective diatomic overlap. It neglects higher order interactions and implies the treatment of electron correlation. AM1 is an improvement upon this by the inclusion of d orbitals in the atomic basis set. RM1 is an improvement upon AM1, as it is just has specific parameters that are made to improve the accuracy of predictions compared to AM1. And PM3 is the most improved and supposed to be the best one of all of them. And it employs a larger basis set compared to all the other ones. It includes things for chemical bonding, molecular interactions. It can predict molecular geometry, energy, spectroscopic properties, etc. It is supposed to be the best one that we can use in our tool set for this experiment. So now going over the results. So di1, di2, di3, and di4 here. Here are the experimental maximum absorption wavelengths, the experimental energies calculated from these wavelengths. And if you want to look at these, I'd suggest you to pause it and look at it, but I'm going to move on for time's sake. So first off, we looked at the particle in a box. So here are the experimental data again. Here is what the particle in a box predicts for the wavelengths and for the energies. And more importantly, here are the percent errors associated with these. Again, I ask you to take the time to pause and look at these percent errors. While the particle in the box is the most crude method, so it is quite high percent errors compared to the other methods, as we will see. Here's the calculated length of the box based off our experimental method. We find that as the length of the box gets longer, the predicted length gets worse. This is most likely due to the fact that as the molecule gets bigger, there's more interactions that are causing bonds to stretch or compress. And that's why we see this different in calculated bond length of the box as we get into the larger molecules. Moving on from the particle in a box, we looked at Huckel. So this is just those electronic energy diagrams of for the Huckel approximation using that Python code to solve for these beta values. And we can see that as we get more more pi electrons, these beta values actually end up getting closer and closer in energy between electronic energy levels. And here we can see we have the HOMO and the LUMO, and we can calculate the difference in the coefficients between the HOMO and the LUMO, called the delta coefficient, which we can see here. That beta coefficient difference between the LUMO and the HOMO can be used to calculate a rough estimate of beta, because we can plot the delta coefficient versus the experimental energy, and the slope is supposed to be the value of beta. So we can see that the values of beta are summarized here in this table. And we can compare this to the literature value of beta, which is right here. So we see some differences, and this is most likely the differences arise to the fact that Huckel is just an approximation and we're not, covering everything. So, and lastly, we can take this beta coefficient or this beta literature and multiply it by the delta coefficient, and we can calculate the Huckel molecular orbital excitation energy. Again, we can compare this to our experimental energies and calculate these percent errors. Again, I ask you to pause these and look at them. But as we can see in general, compared to the particle in a box, these percent errors are lower because the Huckel approximation is a better approximation than the particle in a box. So we would expect lower percent errors. And lastly, we got into the Hartree-Fock methods, where we have di1, di2, di3, di4, which are the same on all these graphs. And essentially what we did is we took the maximum absorption wavelength of each die and we calculated the energies, as well as the wavelengths, which I will get into right now, and we'll see how they compare to our experimental methods. So here are the wavelengths for each method, for each die. And then with the associated percent errors, again, I ask you to pause and look at these yourself, but I'm going to move on to the energies, as I feel like that's what is more important. So here are the experimental energies as predicted by these molecular modeling theoretical calculations. So here are the energies for each method for each die, and then the associated energies for each method for each die. And we can see that in general, we get lower percent errors. We get some high ones, but in general, the percent errors are lower than what we expected. I'm going to move on to this table here, which is our final result, which is the average percent error in energy over all dye compounds, which is for the particle in a box, the HMMO, the MNDO, the AM1, the RM1, and the PM3. We see that of all of these, the one with the lowest average percent error in calculating the energy prediction is RM1. We didn't really expect this because PM3 is supposed to be the gold standard best model, but we are not unhappy with this result. So for a brief discussion, as predicted, the dyes with longer conjugated bond lengths had a higher maximum absorption of wavelengths. So these are increasing carbon bond lengths. And as we see, each one, as we go increasing the length, has a higher maximum absorption wavelength. While not all the theoretical models were better than the other methods, it was found that RM1 as a model was the most accurate predictor of the electronic transition energy. RM1 providing the most accurate result is somewhat surprising because each model is supposed to be an improvement on the previous model. And for this reason, we would have expected PM3 to give the best and most accurate results as the most developed theoretical model. However, we are not unhappy seeing that RM1 is the best model. There could be various reasons why PM3 is not the best. Maybe it's better for larger molecules and not like dyes, things larger than dyes, but RM1 is still a very advanced model, and we're not surprised to see the accuracy of its results. And now just quickly comparing the particle in a box to the Huckel to RM1. So we expected these Hartree-Fock models to give the most accurate results, which is what we found. This is because these models take into account more than just the 2p electron delocalization, which is what the Huckel only takes into account is 2p electron delocalization. And as I said, Huckel, we expected to be somewhat accurate, but not as accurate because it can never be entirely accurate due to the fact that it's just an approximation. We're not looking at things like electron-electron repulsion, and it doesn't take into account the interactions between non-interfering atoms. And we expected both of those to be much better than the particle in the box because the particle in the box is the most crude model we have, where it just confines the electrons to a fixed 1D box, neglecting interactions and geometry among the electrons. So we expected that to have the worst prediction, and that's exactly what we found in our results. So for some sources of error, not all methods accurately encompass everything that's happening within a specific dye molecule. As I said, we're using parameters and setting specific approximations. So not everything is going to account for the entire molecule, all the interactions. So it's really hard to get a completely perfect prediction. We also had some difficulty in setting up the optics for the experiment. We found that setting it up to get the light to exactly hit the director for our peak wavelength was a little difficult, which could affect our maximum absorption wavelength and then propagate throughout the experiment through the energies and the percent errors, which we calculated. And we also thought that more trial runs might be better for each dye, because as we know, if we can get more trials of each dye, we can take an average of all the peak wavelengths and then an average of all the energies and get maybe a better overall calculation for these HOMO-LUMO energy transitions. And so the importance of this and some future suggestions is that it proves that we can use computational methods to somewhat accurately predict the excitation energies of conjugated dye molecules. In the future, we would use a more advanced molecular modeling theoretical model. But as I mentioned, computational time is a concern. As these models get more advanced, normal computers take a very, very long time to perform these calculations, and you often need quantum computers to do these calculations, and it's very difficult to get your hands on those. And we also would like to see a similar experiment performed and with computational predictions and experimental setup with dye molecules that function through aromatic rings, because there's many dyes that use aromatic rings to absorb light rather than conjugated carbon chains. And we'd like to see if we could include those in an experiment and see if we could get similar predictions and similar percent errors. We would just like to thank Dr. Wagner and the University of Pittsburgh for providing all the resources for this lab. And I hope that this lab has given you some insight on how we can use computational methods to predict experimental values and then take experimental values and predict those and compare those against the computational methods. And with that, determine which computational method is the best at predicting experimental values. And maybe that can give some insight on where to move forward with computational methods in the future. Thank you so much for listening and have a great day.